torque and angular acceleration. We're familiar with Newton's second law. The law says force net, this is the sum of all forces, is equal to mass acceleration. And these are vectors, we know them, they're vectors, right? So Newton's second law tells us the acceleration is due to the net force. And this is for translational motion. So for rotational motion, we have a similar law, Newton's second law of rotation. So we'll have a net torque, which is the sum of all torques, that is equal to mass is replaced by rotational inertia, acceleration by angular acceleration. We can still put the vector signs on the torques and the angular acceleration, but at the introductory level, all of these are along either the same direction or opposite direction because we're only discussing rotation around a single axis. So that's equivalent to translation along a single coordinate axis, such as a one-dimensional motion. So it's not necessary to put the vector signs on, but it's nice to know that they're actually vectors. So now we know how torque is affecting the angular acceleration. We should do an example just to try this out. So I have two examples here, and these are solid disks. They're the same exact solid disks. They're just, let's just say that you cut out two exactly the same solid disks out of maybe cardboard. And you have two separate color pin that you're pinning the discs onto a corkboard. So for this one left piece is pinned down here. Let's call this point C. And then let's find the center line, okay, halfway point right here between C and the right side. Let's call this A. So we'll apply the force at A, maybe just poke a hole here and put a string through the hole, and then we can have a force applied at A. Let's use a simple just a force like this. Okay, so we have force F A, that's force applied at A, and the force has a magnitude of 32 newtons. So let's write in between the two diagrams. The situations are the same. So FA has a magnitude of 32 newtons. I'll also do an FA over here. Let's draw some horizontal lines to help us here. Here's a horizontal line. So here we'll have a horizontal line. Goes all the way here, and we'll have a vertical line drawn all the way up to this point. Okay, so the applied force is applied at the same exact point and with the same exact magnitude. So here's A, here's C, here I have a different spot, this is O. Alright, so just imagine trying to do this experiment with two separate disks. And let's say that the mass of the disk, apparently probably not from cardboard, let's see, I have a value I picked, 1.5 kilograms. And the radius of the disk is 0.2 meters with the force given, and also the distance CA, so that's the distance is 0.1 meters, so that's basically halfway. Apparently OA is equal to R. So the goal is to find out the torque in both cases and the angular acceleration in both cases. So first let's look at this formula here. So we have torque on one side, we have rotational inertia on the other side. So as we know from a previous discussion that torque depends on the axis of rotation, because the lever arm's length depends on that, and even the sign of the torque, positive or negative, depends on where the axis of rotation is chosen. So this is arbitrary until you choose the axis of rotation. And the same thing can be said about the rotational inertia. If you're rotating around a different axis, your rotational inertia will be different. And it will likely increase if you switch from a center of mass axis to another axis that's not a center of mass. The rotational inertia will definitely increase. So these two are both with respect to an axis of rotation. So they're both. And we must choose the same exact axis of rotation for them to be consistent. So the same axis of rotation. Let's practice that. It's easier said than done. So let's practice on the left side. And because the axis of rotation is so important, we should start by making that choice explicitly right away. So I'll just say axis of rotation. And because we have this red pin here pinning down this so-called cardboard, let's just say a cutout, maybe it's a wooden cutout disc, and there's a hole here. I pinned it on the corkboard. So the axis of rotation, let's say that's equal to C. So we're placing the axis of rotation right here at the pin. So what does that do? That determines the lever arm now. Because we have this apparent 90-degree angle in both cases, right? So the lever arm, which is equal to the perpendicular distance between the axis of rotation and the line of action of force. This is a force. The line of action extends downward and upward indefinitely. So it is a line. And this line of action and the axis of rotation has this perpendicular distance. So this happens to be the lever arm LA for FA. So this lever arm LA is equal to just CA, the length of this section, right? So this is equal to 0.1 meters. So after I have the axis of rotation, I can say this. And I can also determine the rotational inertia around this axis of rotation. And this axis of rotation seems to be the center. The center mass is right here. So this rotational inertia is the rotational inertia around the center of mass. For a disk, rotating around the center of mass gives you 1/2 mr squared. Right, I can calculate this out. It's going to be 1/2 times 1/2 is 0.75. 0.75 times square of 0.2 is 0.04. 0.04 times 0.75, that's 3/4 of 0.04. So it's 0.03 kilograms meter squared. Wow, this is very close to one of those rotational inertia that you found in the actual lab, except that lab has a much heavier disk, but it's much smaller in radius. So we have this. This number is actually quite big in rotational inertia unit. All right, so we have this rotational inertia. We can calculate the torque. So torque from A is equal to this force A times its lever arm. And it is positive because imagine the force is pulling this way, and it'll cause the disc to rotate counterclockwise around the center of this axis of rotation where it's pinned. So the counterclockwise rotation is positive. And this gives us 32 newtons times 0.1 meters. So 3.2 Newton meter, and let's not write that as a joule, although a Newton times a meter in energy context is a joule. You push with a force, and for sustain that force for a duration, for a displacement, and this is not, you are not sustaining a force for a distance traveled, right? You're just pulling a force a certain distance away. So now we have the torque. We can calculate according to the Newton's second law. This is Newton's second law in rotation. we can find out the angular acceleration. Okay, so the angular acceleration is equal to torque over rotational inertia. So let's be clear, this torque here with respect to the which axis of rotation, the center of mass version, right? This is also with respect to the center of mass version. So let's be a little bit redundant and just mention that. So 3.2 divided by 0.03. So if you use a calculator and just keep 2 to 3 decimal places, let's keep 3 decimal places. And this gives you 107 readings per second squared. Okay, so now let's apply the same exact force to the same exact disk, except that I will pin the disk at this point O on the left side, on the perimeter of the disk. So what happens here? Well, here I need to choose the axis of rotation. Just like I did before, I did this first. This is a very important step. Without choosing the step, you could get easily confused. Okay, so where do I choose it? I could still choose C, right? I could still choose C, but what is the disadvantage of choosing C? Well, let's choose C. We'll later change it. So if the axis of rotation is here, then what about the pin? Well, the pin actually exerts a force on this wooden disc. Imagine you have a cork board and you pin the disc with this pin. Well, the weight of this wooden disc will weigh down on everything, right? This pin gets pulled down. It has to stay without being pulled down, right? So there has to be a support force right here. The reason that we didn't discuss this with the red pin was because we picked the axis of rotation to be right here. Whatever force of support that this pin exerts, the force goes through the choice of axis of rotation. So there's no lever arm on that force. So there's no torque on that force. So if we picked an axis of rotation that is not on this physical axle that the object would be rotating, then we'll be opening up to this complication that there's an unknown force here that we have to consider the torque for it. So are we ready for that? I don't think we're ready on this note. So we'd rather just delay that for the next discussion. So this is not really the good choice because it allows this unknown force at the hinge, the pin, whatever axle that the object actually rotates around. This force at that point to have a torque, and this is an unknown force. We may know the direction, but in other cases we might not even know the direction, let alone the magnitude. So what do? We choose the physical axle to be the axis of rotation right here. Okay, so once we choose this, whatever the pin is supporting with in terms of force has a zero lever arm, so that will be a zero torque. So we only have to consider this force and its torque. Okay, so with that said, let's do this lever arm again. Lever arm of force A. Now that we have a new axis of rotation, the lever arm is going to be distance perpendicular between the axis of rotation and the line of action. So now this is a new LA. It's going to be a distance between O and A now. And that involves one radius and then a half radius. So 0.2 and 0.1. So it's 0.3 together as the lever arm. And what about the rotational inertia? I have some space over here. I'll do that over here. And the rotational inertia, this rotational inertia around O. We have parallel axis theorem to do that. So any rotational inertia can be written as rotational inertia around center of mass plus the mass of the whole object. And here's the distance between the center of mass and the new rotational axis, which is parallel to that center of mass rotational axis. Right? So what is that D? Well, here's the center of mass at C. And how far do we need to move in order to go to the new rotational inertia? A whole radius. Right, so let's just get rid of that and put a curly brace here and put an R here. Alright, so that D, how far do I have to move from center of mass to the new rotational axis? This is AOR. We know that this is also our choice of AOR. And center of mass. Overlapping. The center of mass is an actual position, right? You can calculate with a formula. And an axis rotation is just a mathematical construct. You can pick it anywhere you want. You just have to stick with your choice. Alright, so the distance is equal to R between, this is axis of rotation to center of mass distance, or between. Alright, so let's calculate this rotational inertia. We have 1/2 mr squared for a solid disk through center of mass. Then we have mr squared. So we have 3/2 mr squared. And that will be 3 times as big as the original center of mass rotational inertia right here. So we'll just triple that, 0.09 kilogram meter squared. Alright, so now we know the rotational inertia. We can do the same thing to find rotational angular acceleration. So what we did on the left side was I put together the torque. So torque here, still from force A, is force A times is lever arm A, and that's 32 times the new lever arm 0.3, so that's 3 times as big as the previous time, so it's 9.6 Newton meters. And the angular acceleration is now a torque A around this new axis rotation, which is the O, and rotational inertia also evaluated around the O. So 9.6 divided by 0.09. You may have noticed this. 9.6 is 3 times 3.2, and 0.09 is 3 times the 0.03. So the result is still the same, 107. Wow, that is really strange. Is that something that's predetermined? Well, actually, it's just a coincidence. If you move your axis rotation to a different place, say if you put your pin here, maybe left halfway, and then the angular acceleration will be actually slightly larger than this 107 value. I picked this over here is because it's easy to understand how far you move. You move from center to the edge, right? So the fact that these two are equal is just coincidence where I picked the new axis rotation. So let's review how we did our problem to find out the angular acceleration. So foremost, we picked an axis rotation, and in both cases, the axis rotation we picked is exactly the physical axle around which the object rotates. The reason is otherwise, if you pick a different location, the axle exerts a force, and the force is unknown in magnitude and direction. You have to solve for it. So that's something you may not want to do. So after we picked our axis rotation, we start determining the lever arm lengths for each force's torque. So if we had more forces, we would do several of these lengths, and the length is between the axis rotation and the line of action along which the force vector lie. So once we've done that, a number of the lever arms are calculated, and we also do the rotational inertia. If it's given, that's great. If it's not given, we calculate it. If it's a regular object that we know, such as a disk, we know how it rotates around center of mass, but the axis of rotation is not around center of mass, we need to use parallel axis theorem in order to find the new rotational inertia. So whichever way you find the rotational inertia, easy the center of mass because the situation calls for that, or not so easy to use parallel axis theorem, you find that corresponding rotational inertia with respect to the same axis rotation you were finding those lever arms. And then you can construct your torque together and imagine which way the force, I think I can draw this one over here, which way the force will cause the rotation if it alone applies to the object. So you figure out it's a positive or it's a negative. Counterclockwise is positive. So I had the positive F times L in this situation. If it was clockwise, I would have a negative in front. So then I calculated the torque. And I'll keep going until I calculate all the torques, and then I'll add them together as the sum of the torques. And then once I have the sum, I have the sum divided by the corresponding rotational inertia, I get angular acceleration. Thanks.